two more applications of group theory we are going to discuss in this class. Namely, how to predict an electronic transition will be intense enough or forbidden. And number two, how to find out the hybridization of certain molecules. First, let me take up the electronic spectroscopy. You know that in chromophores, the electronic transition can take place. The possible electronic transitions are a sigma to sigma star transition can take place. It is possible in all the molecules where sigma bond is present. Pi to pi star transition can take place where pi electrons are available, and n to pi star transition can take place where non-bonding electrons or lone pair of electrons are present in a chromophore. These are the three possible transitions that can take place in electronic spectroscopy. Are they allowed or forbidden, or what are the selection rules governing this? There are three selection rules which govern this. One is what is called a spin selection rule. Namely, during electronic transition, spin multiplicity should not change. If the ground state is a singlet, the excited state should also be a singlet. If the ground state is a triplet, the excited state should also be a triplet. These are the allowed transitions. Whereas a singlet to triplet and triplet to singlet these are forbidden transitions. They cannot take place. This is one selection rule which governs the electronic transitions in chromophores. The next selection rule is what is called a Laporte selection rule. In molecules containing a central symmetry, an I is there in the molecule. In such a molecule, G to G and U to U, these transitions are forbidden transitions. Whereas G to U and U to G are allowed transitions. G referring to Gerada, U referring to Ungerada. That's the correct pronunciation. It's German terminology. Now, say for example, I have Txy orbital. I can represent like this. If this is X and this is Y, Txy is this. So there is a central symmetry, and plus comes here and plus goes over there. So I is present in this molecule. We get a similar structure. Similarly, X is that. And Y is that. We call them as T2G orbitals. Similarly, you have Z square orbital. And D X square Y square orbital. We call them as EG orbital. So, in complexes where d orbitals are available, a T to G to EG transition is a forbidden transition. Forbidden means it doesn't mean it won't take place. The intensity will be very less. Whereas, if it is from U to G or G to E, U, it is allowed transition. So this is a second selection rule regarding the electronic transitions. The third selection rule is multi-electron transition is forbidden. Multi-electron transition is forbidden. This cannot take place. What I mean to say is, let us say I am talking about a n to pi star transition. In the ground state, there are 2 electrons in the n orbital, lone pair of electron in an unmodified orbital. And the excited state cannot be pi star 2. This is not possible. So excited state is either you must, there is only one possibility. One electron can be excited from n orbital to pi star orbital. So multi-electron transition is forbidden. Similarly, if I talk about a pi to pi star, if my ground state is pi 2, there is no electron in pi star, excited state has to be pi 1, pi star 1. It cannot be pi 0 and pi star 2. That is not possible. So subject to these 3 selection rules, electronic transition take place. Then, as far as the intensity of the transition is concerned, I is proportional to considering a transition from an orbital A to an orbital B. So I indicate the intensity of the transition like this, where M is a dipole moment operator. M is a dipole moment operator. This dipole moment operator can be split into 3 components, namely if any one of them is non-zero, then intensity will be there. Such a transition is symmetrically allowed transition. What is this mx, my, mz? As I told you, it is a dipole moment operator along the x-axis, y-axis and the z-axis. says that for any one of them to be non-zero, if you multiply the symmetry of the ground state, symmetry of the excited state, and symmetry of the Cartesian coordinate, if this is equal to A1, then such a transition is an allowed transition. I said that symmetry selection rule says symmetry of the ground state, symmetry of a Cartesian coordinate and symmetry of the excited state, this should be equal to a totally symmetric representation A1. Then this integral will not be equal to 0. Such a transition is an allowed transition. If it is not equal to A1, then it is a forbidden transition. Let me take a simple case and explain this. Say for example, I am talking about a sigma to sigma star transition. In the ground state, 2 electrons are there in the sigma orbital, and in the excited state, 1 electron is promoted to sigma star. Is this transition symmetrically allowed transition or not? For that, you must find out what is the symmetry of the ground state and what is the symmetry of the excited state. What is the symmetry of the sigma orbital? Well, we can find out very easily now. Let me consider a molecule like formaldehyde. A molecule like formaldehyde. It belongs to C2V symmetry. You know what are the operations in the C2V point group? An identity operation is there, a C2 operation is there, a sigma xz and a sigma yz. These are the 4 operations. So I am going to perform these operations on the orbital which is in question and find out what is the symmetry of this orbital. Let me tell you, the coordinates are like this. The molecule is like this. Namely, if this is the x-axis, this is the z-axis, and this is the y-axis. So, this is z. This is y. And this is x. That means the molecule, all the atoms are in the yz plane. This is xz plane and this is yz plane, and the atoms are all in this yz plane. Now let me sketch the sigma orbital. I said this is x, this is z, and this is y. The sigma orbital in formaldehyde is like this. This is the sigma orbital, shape of the sigma orbital. Let me perform all the operations on this molecule. Identity, nothing happens. So it is 1. C2, I am giving a 180 degree rotation. The molecule is originally like this, now it is like this. So, no change in the sign of the wave function, it is +1. Sigma xz, I am going to reflect in this plane. The molecule is like this. This is sigma xz, I reflect in this plane. Nothing happens, it is 1. Sigma yz. So this is the molecule, and YZ plane is the same plane. So I reflect in YZ plane, nothing happens. So that is also 1 again. That's also 1 again. So sigma orbital belongs to A1 symmetry. Let me make a note of it. Sigma belongs to A1. Now about the sigma star. Sigma star is like this. Don't forget the molecule is in this plane. I perform identity operation. Nothing happens. C2. I put an axis here and give a 180 degree rotation. Nothing happens. Sigma xz. I reflect in this plane. Nothing happens. And sigma yz. I reflect in this plane. This is the molecular plane, and the same thing, yz plane. Nothing happens. So sigma star, the anti-bonding sigma orbital, also belongs to the A1 type. So sigma star belongs to A1. Now, how about pi? I sketch the pi orbital of this molecule. This is the molecular plane. We have a positive lobe here and a negative lobe here. I carry out identity operation. Nothing happens. I carry out a C2. That means this is the z-axis is the axis I set. I give a 180 degree rotation, it will become -1. Sigma xz. I reflect in this plane. The molecule is like this. A positive lobe above and a negative lobe below. I reflect in this plane. Nothing will happen. So sigma xz, it is +1 again. Sigma yz. I put a mirror here and reflect. The minus goes up and the plus comes down. So it is -1. You can refer to the character table of C2V point group. 1 minus 1, 1 minus 1 corresponds to B1 symmetry. So I will write it as pi belongs to B1. Now about pi star. I am sketching the pi star orbital now. This is the pi star. The molecule is like this. You have a positive lobe here, a negative lobe here. A negative and a positive. I perform all the operations. Identity. Nothing will happen. C2. This is my axis. I put a C2 and give a rotation. So minus will become plus, plus will become minus, so it is -1. Sigma xz. The molecule is like this. I put a mirror here and reflect. Nothing will happen. So it is +1. Sigma yz. I put a mirror here and reflect. The minus goes above, plus comes down. Plus goes above, minus comes down. So it is minus 1 again. 1 minus 1, 1 minus 1 belongs to B1 symmetry. So pi star belongs to B1 symmetry. So sigma and sigma star both A1, pi and pi star both B1. Then a non-bonding, a lone pair of electrons is present on the oxygen. I am sketching that. It will be better just to show it is behind the board. This one is projecting towards and that is behind. Okay. Now, I carry out identity. Nothing will happen, it will be there. I carry out in C2. This is my axis. If I give a 180 degree rotation, plus will go above, this will go behind and that will come in front. So it is minus 1. Sigma xz, I reflect in this plane. Again the plus will go behind, minus will come, so it will be minus 1. Sigma yz, it is a molecular plane itself. So plus is here, minus is here, I put a mirror here and reflect. Nothing will happen. So the characters are 1, minus 1, minus 1, 1. If you refer to the character table, this belongs to B2 symmetry. So the non-bonding electrons, or the lone pair of electrons, belong to B2. So I have found out the symmetry of the various orbital where the electron transition is going to occur. I said that. Suppose I talk about a sigma to sigma star transition. I told you what is the symmetry of the ground state and what is the symmetry of the excited state. Ground state is both the electrons are in the sigma orbital. The excited state is one electron in the sigma and one electron in the sigma star. This is the excited state. What is the symmetry of this and what is the symmetry of this? Symmetry of sigma belongs to A1. There are two electrons, so it is A1 into A1. The ground state is A1. How about the excited state? You have one electron in the sigma, one electron in the sigma star. Sigma belongs to A1, sigma star belongs to A1 into A1. The excited state is also A1. I told you the rule, symmetry of the ground state, symmetry of any of the Cartesian coordinate into symmetry of the excited state should be equal to A1. Symmetry of the ground state is A1. This is the ground state. Symmetry of the excited state is also A1. Is there any Cartesian coordinate which belongs to A1 symmetry? If you look at the character table, that tells you Z coordinate belongs to A1. So A1 into A1 into A1 is A1. So sigma to sigma star transition is an all-round transition. Similarly, let me find out about pi to pi star transition. So my ground state is 2 electrons in the pi orbital. My excited state is 1 electron in the pi orbital and 1 electron in the pi star orbital. Find out the symmetry. Pi orbital belongs to B1 symmetry. So the ground state is B1 for 1 electron, B1 for the other electron. You know B1 into B1 equal to A1. We have already seen all those things. So the ground state is A1. Excited state, one electron in the pi, one electron in the pi star. Again, it is B1 into B1, A1. So, symmetry of the ground state is A1. Symmetry of the excited state is A1. Symmetry of any of the Cartesian coordinate which belong to A1. Yes, Z coordinate belongs to A1. So the product is A1. So the transition is allowed transition. So sigma to sigma star is allowed. Pi to pi star is allowed. One more thing remaining is N to pi star. So I am finding out the symmetries of the N and the pi star. My ground state is N2. And the excited state is one electron in the N, one electron in the pi star. N belongs to B2 type. So N2 means B2 for one electron, B2 for the other electron also. So this is A1. My ground state is A1. Excited state. N1 belongs to B2 and the pi star belongs to B1. B2 into B1 is A2. Just to illustrate, I am telling you, B2 is nothing but 1 minus 1 minus 1 1. And B1 is nothing but 1 minus 1 1 minus 1. It is a direct product. B2 into B1 equal to 1 into 1 1. Minus 1 into minus 1 1. Minus 1 into 1 minus 1. 1 into minus 1 minus 1. 1 1 minus 1 belongs to A2 symmetry. That's what I have written here. So my ground state is A1. Excited state is A2. Is there any Cartesian coordinate which belongs to A2? Only then A2 into A2 will be A1, A1 into A1 will be A1. If you look at the character table, none of the Cartesian coordinate belongs to A2 type. Z coordinate belongs to A1, X coordinate belongs to B1, Y coordinate belongs to B2. Look at the character table, you can find out that. And none of the Cartesian coordinate belongs to A2 type. So there is no coordinate belonging to A2. That means this product may not be equal to A1. That means this transition is a forbidden transition. So N to pi star in formaldehyde, N to pi star in formaldehyde is a forbidden transition. Sigma to sigma star is allowed. It's a very high energy. You will not be able to see it in the visible region at all. Pi star in formaldehyde, N to pi star is a forbidden transition. Sigma to sigma star is allowed. Pi to pi star is allowed. N to pi star is forbidden. A forbidden transition means the intensity will be low. You can't say the transition doesn't take place at all. It takes place, but it's a low intensity. So if pi to pi star is like this, N to pi star will be of less intensity. Hence, from a knowledge of group theory, you'll be able to predict in a chromatophore what are the transitions which are allowed and which are forbidden. All such information could be obtained if we have a knowledge of the group theory. The next application is about finding out the hybridization in a molecule. Say for example, I have a molecule like BF3. It is a planar molecule belonging to D3H symmetry. The operations that are present in this molecule are an identity operation. A C31 and C32 both belong to the same class, so I write it as 2C3, and 3C2 Each BF bond is a C2 axis. So 3 C2 are there. And a sigma H, a horizontal plane, is there. And you have 2s3 operation in this molecule. And 3 sigma operation is each bond, BF bond, acts as a planar symmetry. So totally 3 plus 2 plus 1 plus 3 plus 2 plus 1, 12 operations are there. So order of this group is 12. How many classes are there? E is a class, the 2C3 belong to a class, 3C2 belong to a class, sigma H is a separate class by itself, 2S3 belong to a class, and 3 sigma belong to a class. So totally 6 classes are there. Order is 12 and class is 6. When I say class is 6, you understand there are 6 irreducible representations in this molecule. They are A1 prime, A2 prime, E prime, A1 double prime, A2 double prime, and E double prime. These are the 6 irreducible representations for this molecule. You can look in the character table of D3H and you will get this information. Now what I do is, I perform all the operations on this molecule and find out how many bonds remain unshifted. So the bonds are formed by the hybridization. So in the case of IR, we found out how many atoms remain unshifted. Whereas here, find out how many bonds remain unshifted. So number of unshifted bonds. Identity operation, all the 3 bonds remain unshifted. When I do a C3 operation, all the bonds get shifted. So number of unshifted bonds is 0. I perform a C2 operation, put an axis here and give a 180 degree rotation. This bond around will be unshifted, these 2 exchange positions. So when I do a C2 operation, only 1 bond remains unshifted. A sigma H, I reflect in this plane, all the 3 remain unshifted. S3, a C3 followed by sigma. When I do C3 itself, the bonds get shifted. So it is 0. And if I reflect in a plane, that bond, only 1 bond will be unshifted. These 2 bonds will exchange positions. So it is only 1. So 301 is the reducible, this itself is a reducible representation. The number of unshifted bonds which you get itself is a reducible representation. So the reducible representation is 3, 0, 1, 3, 0, 1. Now I find out how many A1 primes are present in this. How many A2 primes are present, E primes are present, A1 double prime, A2 double prime, E double prime. How many are present in this? For this we use the formula. You know the reduction formula. The reduction formula is 1 by H. Sigma N, number of times that particular operation occurs. Character in the reducible representation into character in the irreducible representation. This is the reduction formula to reduce a reducible representation into irreducible representations. So let me use this formula, find out how many A1 primes are there, A2 primes are there, E primes are there, A2 double prime, E double prime, A1 double prime, everything I can find out now. So let us look into that procedure now. First I am going to find out how many A1 primes are there? If you look at the D3H character table, the characters for A1 prime is 1, 1, 1, 1, 1, 1. All are plus 1. So let me find out how many A1 primes are present in this. I use the formula, order is 12, 1 by 12. Only 1 is there, 1 into 3 into 1 plus 2 into 0 into 1 plus 3 into 1 into 1 plus 1 into 3 into 1 plus 2 into 0 into 1 plus 3 into 1 into 1. So that is equal to 3, 0, 3, 3, 0, 3. That is equal to 12 by 12, 1. So this contains 1 A1 prime. I find out how many A2 primes are there. Irreducible representation A2 prime. I'll find out how many A2 primes are there present in this. 1 by 12. 1 into 3 into 1 plus 2 into 0 into 1. It is going to be 0. I need not write anything. Going to waste time. 3 into 1 into minus 1. 1 into 3 into 1. This is 0, I leave it. 3 into 1 into minus 1. That is equal to 3 minus 3, 3 minus 3, 0. So this doesn't contain any A2 prime. This reducible representation doesn't contain any A2 prime. We have found out that there is only one A1 prime in this. Then I find out how many E primes are there. How many E primes are there? The characters of the irreducible representation E prime is 2, minus 1, 0, 2, minus 1, 0. So let me find out how many E primes are present in this. 1 by 12 into 1 into 3 into 2 plus 2 into 0 into minus 1, 0, I leave it. 3 into 1 into 0, 0, I leave it. 1 into 3 into 2. This again is 0. This again is 0. So that is equal to 1 by 12. 6 plus 6 equal to 1. So this contains 1 E prime. 1 A1 prime and 1 E prime. Let me find out how many A1 double primes are present in this. How many A1 double primes are present in this? The character for A1 double prime in the irreducible representation is 1, 1, 1, minus 1, minus 1, minus 1. These are the characters for A1 double prime. So let me find out how many A1 double prime is included in this reducible representation. 1 into 3 into 1 by 12 into 1 into 3 into 1. This is 0, I leave it. Plus 3 into 1 into 1. Plus 1 into 3 into minus 1. This I leave 0 because it is 0. Plus 3 into 1 into minus 1. That is equal to 1 by 12. 3 plus 3 minus 3 minus 3. Again, this is 0. So this doesn't contain any A1 double prime. Let me find out how many A2 double primes are there. How many A2 double primes are there? Look at the D3H character table. Find out what are the characters for A2 double prime. For A2 double prime, the characters are 1 1 minus 1 minus 1 minus 1 1. This is the characters of reducible. I am writing the characters of irreducible. 1 1 minus 1 minus 1 minus 1 1. So let me calculate now. 1 by 12. 1 into 3 into 1. This will be 0, I leave it. 3 into 1 into minus 1. Plus 1 into 3 into minus 1. This will be 0, I leave it. 3 into 1 into 1. That is equal to 1 by 12 into 3 minus 3 minus 3 plus 3. This array is equal to 0. See, this doesn't contain any A2 double prime. Is there any E double prime? Let me find out that also. Character table of D3H tells me the characters for E double prime is 2 minus 1 0 minus 2 1 0. These are the characters for E double prime. Therefore, how many E double prime are contained in this? 1 by 12 into 1 into 3 into 2. This is 0, I leave it. This is 0, I leave it. 1 into 3 into minus 2. This is 0. This is 0. So it is 1 by 12 into 6 minus 6. This again is 0. That's all. So if you reduce this reducible representation, I get one A1 prime and one E prime. So I must look for the orbitals which belong to this symmetry. If you look at the character table of D3H, look at the third column, you can find out which orbital belongs to this. Of course, we know that S orbital is totally symmetric. That belongs to A1 prime. As far as the E prime is concerned, the column 3 in the character table tells me that orbitals Px and Py belong to this type. If you look at the fourth column, the quadratic functions, xy and x square y square belong to this. So dxy orbital and dx square y square orbital belong to this. Therefore, the possible hybridizations are sp2 or sd2. sp2 or sd2. Energy conservations tell me that d orbital is of high energy. You can't promote this to d orbital and involve in hybridization. So sp2 is ruled out. So the hybridization in boron trifluoride is sp2. So thus, group PV tells us what are all the vibrations which are infrared active, which are Raman active, what are all the electronic transitions possible in a chromophore, and we can even find out what is the hybridization involved in a molecule. So that finishes the applications of the group theory.